Next result is also interesting, which shows the Riemann integral functions integral can be calculated as if it is a definite integral under certain restriction. So, assume alpha increases monotonically and alpha dash is a Riemann integral function on is a Riemann, this we say is a Riemann integrable function, belongs to Riemann integrable function, we denoted by this. Okay. So, alpha dash belongs to the class of Riemann integrable function, this on AB. Let f be a bounded real function defined on the closed interval a b. Then the result says f is in Riemann-Stieltjes integral with respect to alpha if and only if the f into alpha dash, this product is Riemann integrable function. It belongs to the class of Riemann integrable functions on a b, and in that case the integral a to b f d alpha, Riemann-Stieltjes integral of the function f, is the same as a to b f x into alpha dash x d x, as if it is just a definite integral when the function is like this Riemann. Okay. So, this same test. Let us see the proof of this. Let epsilon r greater than 0 be given. Okay. Now, given that since alpha dash belongs to the Riemann integral functions over the interval a b, so by definition there is a partition. So, there exists a partition or there is a partition P, say x naught, x 1, x 2, x n of a b, such that the upper sum of the function alpha dash minus lower sum of the function alpha dash with respect to the partition P is less than. By necessary and sufficient condition for a function to be the Riemann integral is the difference between upper sum minus lower sum will remain less. There will be a partition where the difference fluctuation of the function will remain less than epsilon. This is the fluctuation of the function. So, okay. So, let it be 1. Okay. Now, since alpha dash is giving to be, since alpha dash means is a differentiable function, alpha dash belongs to R, which is differentiable. It belongs to, I mean, it exists, so it is differentiable. So, it implies that alpha is continuous. Alpha dash is continuous, because if every continuous, if the function is different, it has to be continuous. So, alpha dash will be a that is a continuous function, alpha will be a continuous function, otherwise we cannot talk about the derivative. Since alpha dash exists, it means this shows that alpha is differentiable, So, alpha must be continuous, that is the main from here, because this is given alpha dash means derivative of alpha. So, this exists. So, it must alpha must be a continuous, otherwise the derivative cannot be, if it is discontinuous cannot be talk about the differentiability. So, alpha is continuous. So, alpha is continuous throughout the interval a b. So, this is the interval a b, and partitioning we are choosing the partition, say x minus 1 and x I, this is the partition. So, alpha is continuous on the partition. So, alpha is continuous on the closed interval x I minus 1 x I for each I. It is differentiable on the open interval x I minus 1 x I. So, by mean value theorem, Lagrange's mean value theorem, we say alpha x I minus alpha x I minus 1 must be equal to the derivative of the function alpha dash at a point say t I delta x I, where the t I lies between x I minus 1 to x I, is it not? So, there exists a point, now this may be closed also. Okay. So, t I will be for some, there exists a some point t I where this will exist by mean value theorem. So, let it be this say number 2 okay, for each I, and this is 2 for each I 1 to n 2. Now, what is given is that our alpha is an increasing monotonic function, alpha dash is this, and f be a bounded linear function, then f if only this. Okay. So, let us take the point, suppose this is x I minus 1, here is x I and t I is somewhere. So, let us choose the point s I, choose a point s I belongs to x I minus 1 to x I. Then let us apply that result. What this result is, which we have proved earlier, the result is this one. Result says if, then by the result, by the theorem which we have proved earlier, the theorem is, what theorem is, if the partition, if u p alpha f alpha minus L p f alpha is less than epsilon. If for every epsilon there exists a partition, if for every epsilon greater than 0 there exists a partition p such that this holds, such that this holds, then, and if s I and t I are arbitrary points, are arbitrarily points in the interval x I minus 1 to x I, then this sum sigma I is equal to 1 to n mod of f s I minus f t I into delta alpha I is less than epsilon. This result we have already proved. So, using this result, because our function alpha I is giving to be continuous function, bounded is giving satisfying this condition. Okay. So, for any partition p we can get this. So, what we did, apply the condition alpha dash, because alpha dash, one more thing is that this shows that if alpha is a function f must be in R, if and only if. Okay. So, this shows that this is f in R, f belongs to R alpha if and only if this result is true. So, what is the alpha dash is in R, alpha dash is in R. So, we can get this result quickly. So, by the result, if S I be any point of this, then by this theorem, by the theorem stated above, we get immediately sigma I is equal to 1 to n alpha dash S I minus alpha dash T I into delta x I is less than epsilon. is less than epsilon, and because alpha dash is in R alpha, is in R on A B. This is given, and that is why this result is valid. Okay. So, let it be condition 3. Okay. Now, since our this sum sigma I is equal to 1 to n f of S I delta alpha I, this is nothing but what? Sigma I equal to 1 to n f of S I delta alpha I, we have already proved it in the second. This is our delta alpha I, is it not? So, this delta alpha I, which is equal to say delta alpha I, is nothing but alpha dash T I delta x I. So, by using the second, we can say this is equal to alpha dash I T I delta x I by second. Okay. Then consider this sigma I is 1 to n f of S I delta alpha I minus sigma I is 1 to n f of S I alpha dash S I into delta x I. Okay. Consider this thing. Now, we have already shown this part, is it? The sigma f I delta I is this thing. So, here is T I. So, what I say? I subtract this thing T I and add T I. So, if I subtract T I and add, so let it be 4. So, using 4, consider this. Now, this can be written as add mod sigma I is 1 to n f of S I delta alpha I minus sigma I is 1 to n f of S I alpha I dash T I delta x I plus sigma I is 1 to n f of S I alpha I dash T I delta x I minus sigma I is 1 to n f of S I alpha dash S I delta x I. Just add and subtract. Now, this part is exactly same as this. So, this will go to 0. Now, this is there, but because of this we get the earlier one result alpha dash I minus this because of the 3. So, apply the 3 condition. So, this is less than epsilon and f is bounded. So, can you not say this is less than equal to m epsilon by third, and m is supremum value of mod f x because of this. Okay. So, in particular we can say this. So, let it be. So, what we get is, so we get basically this result sigma I is equal to 1 to n f of S I delta alpha I is less than equal to m plus f, sorry, m into epsilon, m epsilon plus sigma I is 1 to n f of S I alpha dash that is what he is saying, is it not? F of S I alpha dash I, f of dash this thing, this part, and f of S I you can taken outside. So, what you are getting is f of S I delta alpha I minus this part. So, minus this part is less than epsilon. So, this thing is less than equal to this plus this. So, f of S I alpha dash S I delta x I, this is true. So, which we get from here. So, we get this thing. Now, this is true for what? For every I and S. So, if I replace this by the upper sum of this. So, for all choices of S I which is in x I minus 1 to x I, this result is whole. So, you take the upper bound for this. So, once you take the upper bound, so that we get what? This is less than equal to m epsilon plus the upper bound of the function f alpha dash, because this is the f alpha dash function. So, replace this by its maximum value. So, you are getting the upper bound for this, and which is less than equal to I is greater than equal to 1 to n f of s I delta alpha y. Now, take the upper bound for this. So, now take the upper bound left hand side, take upper replace by this maximum value. So, you are getting this is true for every s I. So, we get the upper bound of this f alpha is less than equal to upper bound of f alpha dash plus m epsilon. Let it be say fifth. Now, in a similar way we can also use this thing. If I take this is less than epsilon naught, so this part is less than equal to this, greater than equal to this minus epsilon naught. So, from similarly we can say similarly same argument we can say that upper sum of p f alpha dash is less than equal to upper sum of p f alpha plus m epsilon in a similar way from the same inequality. Therefore, the difference of this upper sum of p f alpha minus upper sum of p f alpha dash is less than equal to m epsilon. Okay. Clear? Now, if we take this is 2. So, what you get? Take the infimum value of this, take the infimum. So, take infimum over all the partition P. So, this will lead to the integral a to b upper sum f d alpha, this will lead to the integral a to b bar f x alpha dash x dx, and this entire thing is less than or equal to m epsilon. But epsilon is arbitrary, but epsilon is arbitrary small number. So, as epsilon goes to 0, we get integral a to b bar f d alpha is nothing but the a to b upper sum of this upper sum of f x alpha dash x dx. Okay. Let us see. Similarly, for any bounded function, this is true for any bounded function. Similarly, we can prove the lower integrals. Similarly, we can show that a bar f say a bar of this part, that is a bar of f d alpha is the same as a lower bar b f x alpha dash x dx. So, 8 and 7 and 8 implies if f is given, what is given is that function alpha dash is in this and f is giving to be a Riemann-Stieltjes integral, then this left hand side are equal. Therefore, these two are equal and we get integral a to b f d alpha is the same as a to b f x alpha dash x dx. Dx. Okay. So, this improves the result complete. Okay. So, this shows that remark you can say remark is that what the if so what if alpha has an integrable derivatives integrative derivatives, then the integral reduce, then integral reduces to an ordinary Riemann integral. Hence, this can be easily computed. So, this is what we are getting. Okay. So, this almost we have completed. Now, we will give a slight just a concept of what is our measure. We have discussed already earlier, but let us see some in slightly in detail what is the measure and what do you mean by the almost everywhere functions and like this. So, let me just say few concepts. Set of measure 0, set of measure 0. Set of measure 0. Okay. Let us see. We define that the subset E of R, E of R real line, subset E of R is said to be of measure 0, of measure 0 if for each epsilon greater than 0 there exists a finite or countable number of open intervals I1, I2 and so on, such that their countable union covers E, and the length of this, length of I n 1 to infinity is less than epsilon, where L denotes the length of the interval, length of open interval I n of R. Clear? So, what do you mean by that? If suppose a subset E is there, suppose these are the points in E, these are the set E, and if we are able this set E is said to be a measure 0 if B encloses these points by means of an open interval I 1, I 2, say I n and so on, such that length of these open intervals is less than epsilon, such that countable union of this covers E, means all the points of E belongs to the countable union of I n, but the sum of their length is not exceeding by epsilon, then we say the set E has a measure 0 or is said to be of measure 0. Now, thus what we can say is length up to okay. And there is one result which will be useful. The result says if each of the subsets E 1, E 2 and so on of R is of measure 0, then their countable union, that is union of I E n is 1 to infinity is also of measure 0, and this is very easy to prove. But suppose I fix up, proof of this simple, suppose I fix up epsilon greater than 0. Okay. Since E n has a measure 0, so by definition there are the countable for each n belongs to say I is the natural number or some n natural number. Then since E n is measure, so there exists a finite or countable collections, countable number of open intervals which covers E n, and whose lengths add up is less than epsilon, length add up to less than say epsilon over 2n. Okay. Therefore, the countable union un, therefore, countable union of en 1 to infinity is covered by countable union of these intervals of all such open intervals of interval whose length add up to what epsilon by 2 epsilon say first term epsilon 2 square epsilon by 2n and so on. So, if I add this becomes less than epsilon. So, up to less than this number, hence it is a okay. So, this proves as a corollary we can say every countable subset of measure of R has measure 0. Every countable subset, because why the reason is suppose as E is a countable set, we can arrange in the form of the sequence like this. This is a countable set. So, each one x 1 x 2 x n we can enclose it by means of a countable number of n intervals, and sum of this will be each sum is less than epsilon. So, countable union of this sum will also be less than epsilon. So, this is countable. Rational numbers forms a set of measure 0, because rational numbers are countable measure 0. So, this shows this. Now, this is last one which is very important, almost everywhere. A statement is almost everywhere. A statement is said to hold at almost every point of the interval a b or almost everywhere in the interval a b if the set of points of a b at which the statements does not hold is of measure 0. So, that is the definition. So, thus we say, for example, if we say f is continuous at almost every point of the interval a b, means the same as if E is the set of points of a b at which f is not continuous, then E is of measure 0. So, that is what is f is continuous almost everywhere means. Now, based on this we have a very important theorem, and the proof is of course, we are just neglecting, because this proof based on already we have proved this earlier. The theorem says let f be a bounded function on the closed interval, close bounded interval say a b, then f is Riemann integral over interval a b, f is Riemann integrable functions over the interval a b if and only if f is continuous, at almost every point in the interval a b, almost every point in the interval a b. Then we say the function is continuous for this. Okay. For examples, let us take this function. Suppose I define f x as 0 and 1 when x is say x is irrational and x is rational and this is irrational point. Okay. This is bounded function. Now, let us see what type of, we will discuss whether, question is whether f is Riemann integrable functions over 0, 1 or not. So, this question we will discuss next when you go for the tutorials. Okay. Similarly, thank you very much.